Lesson 3.10, Related Rate Problems. What happens in all of these problems is that you will have quantities that are going to change with time, and there are some instances where you're going to have quantities that are fixed versus those that are changing with time. Take a moment and read up at the top the strategies, and then join me for the start of the lesson. You have a 6-meter ladder and it's leaning against a wall. So I have right now my little popsicle sticks that are demoing a wall and the ladder. So what happens is that the bottom of the ladder is going pushed along the ground. Notice you can see the angles changing as the ladder is sliding down the wall. So the distance up on the wall is changing, it's shrinking, and the distance along the ground is increasing. Likewise, if I push the object towards the wall, okay, you can see the angles and the side lengths are changing. That's what this is kind of all about. It's about changing lengths. But notice the ladder itself never changed its length, only the distance along the wall and the distance along the ground. I'm going to make a visual to go along with my problem here. We have the wall, assuming the wall meets the ground, at a perpendicular. Then labeling what we know. 6 meters is a fixed amount, so I'm literally labeling it 6 meters. However, these two lengths are changing. As this moves and this moves, those lengths are changing, so these lengths have to be a variable. You can go with traditional X and traditional Y for variables to represent the side length and the bottom length. All right, what do we know? The bottom of the ladder is pulled along the ground away from the wall at a constant rate of 0.5 meter per second. That means it's heading in that direction. We've got movement. We have growth of the length of X. So to describe that change in the length of X, we would say d for delta. And what is it changing with respect to? It's changing with respect to time. Since I am increasing my distances, this is a positive 1/2 meter per second. If you were going this way towards the wall, you would be shrinking your distance, and then that would be a negative. The question says, how fast will the top of the ladder, here's the top of the ladder, be moving down the wall? Well, if this is going down the wall, that means y is changing. So there's a change in y with respect to time. That is what I'm looking for, so we're going to say it's unknown. And it's unknown, but at the moment I want to know it. The ladder is 3 meters above the ground. So at one moment in time, this y does equal 3. What you do for these problems is you find a connection between what you have, but don't look at the derivatives. Is there a mathematical connection that connects the pieces? Hopefully everybody's thinking, yes, the connection is the Pythagorean theorem. And how you set it up matters. It's x squared plus, now this y is 3, but it's only 3 at a moment. This is a changing length. So to recognize that it's changing, I say plus y squared equals, this is a fixed length, it'll always be 6, there's no change in the length of the ladder. So when things don't change, we put them in as their numeric values. Then what happens is I want to do the derivative of my relationship here, but with respect to time. So we're doing derivative with respect to t. Notice I do not have the variable t in the problem. This is implicit differentiation, but in an application setting. So when I go to do the derivative of x squared, I start off like I normally do. The derivative of x squared is normally 2x. But that's when we take the derivative with respect to x. because I'm deriving with respect to time, we now have implicit and chain rule acting on this. So I'm going to say times the rate at which x is changing with respect to time, plus y squared. I'm going to bring the 2 down in front. I have y, and in implicit differentiation we would have said times y, or dy dx. But this one, I am taking the change in y, but with respect to times. So it's times dy dt equals, and then 36 is a constant. The derivative of any constant always goes to 0. Then I look at the connections I have. Well, I have information about dx dt. That's a 1/2. I have a constant of 2. X, I don't have a label or an acknowledgement of x. I'll go back to that. 2. At the moment we care about, the y value is 3. dy dt is the rate at which it's sliding, so I'm looking for that, and I'm going to set it equal to 0. What happens is sometimes you have missing information when you go to create your equation with the derivative, but you do have techniques to solve and find it. I can use Pythagorean theorem off to the side here and say x squared plus 9 is equal to 36. So the value for x at the moment we care about, that value is the square root of 27. So I'm going to put it in as the square root of 27. Doing some simplifying here, I have a root 27 and we have a 6 dy dt equaling 0. To solve that dy dt, I subtract the root 27, divide by 6, so my official answer is negative root 27 over 6. If it's a multiple choice and you had to do some simplifying, you would simplify that square root. But these problems now need labels. It came out to be negative, which is good because that's indicating I have a decreasing rate, which means the ladder is sliding down. So it's good that it came out to be a negative number. And then the label for it, it's a length that is changing. The lengths are being marked with meters, and time is in seconds. So the rate at which it slides down the wall is negative root 27 over 6 meters per second, or negative 0.866 meters per second, because a lot of times it makes more sense when you have an application problem to think of it like in a visual way. So you're looking at like 9/10 of a meter per second. Take a moment, read this number 2 before watching the video. I have a circle. The oil is spilling out in a circular manner. So what happens is I go back and I read the problem and I look at what the numbers are describing. It's talking about whose area increases. So area is changing at a rate of 5 miles squared per hour. Since it's talking about area increasing, well then I know that there's a change in area with respect to time. That's dA dt. And that equals 5 square miles per hour. How fast? Okay, that's a rate. When you see wording like that, I'm looking for a rate. The rate of who? It talks about the radius. So how fast is the radius increasing? I don't know it, so I'm going to go down here and say, well, there is a radius, but this radius keeps growing and growing and growing as the circle expands. So dr dt is what I am looking for. What else do we know? It's looking for that rate at the moment that that circle has an area of 16 square miles. There's all my information. So to start the problem, what you do is you think about a connection in a circle. If it's talking about changing area and changing radius, then I want to go back to my original circle and connect the radius to the area. That is done by remembering area equals pi r squared in a circle. Then you take your known information, you do its derivative with respect to time. dA dt is equal to, That's a constant being multiplied. So the 2 as a power is coming up in front. So I have 2 pi r to the first, but now the radius is changing over time. So by chain rule, I'm going to say times dr dt. Then I plug in. This is 5, 2 pi. I need a radius, and dr dt is what I'm solving for, so I'm going to keep that as its form. Well, how do I find that radius? I know the area is 16. Well, pi r squared is equal to 16, because that's the area formula. So r is going to be the square root of 16 divided by pi. So I'm going to put 16 divided by pi, in the denominator with my square root around it. Then dr dt becomes 5 divided by this quantity. Now what will happen is if it's a non-calculator question, it's going to end up being simplified. So 2 times the square root of 16 is going to give me 8. And then a pi divided by a root pi, either rationalize or use the rules of exponents, you get the square root of pi. Well, dividing by a fraction is multiplying by its reciprocal, so I get 5 square roots of pi divided by 8. And then the label for it, I just realized something. Got to backtrack here. Okay, so this pi is pi to the first, this pi is pi to the half, so first take away a half is a half, so it actually is 8 times the square root of pi here. So then you could leave it as 5 over 8 square roots of pi, or you could make it 5 root pi over pi. Either one of those answers would be possible. And then the label for it is it's a changing radius. Radius is a linear dimension. So changing radius would be measured in miles, because I make the connection to how area is. Radius is linear. So it would be miles per hour. The next one, again, pause it and read what it's saying and see how much of the information you could pull out yourself. We have a cylindrical tank. The radius of the base, right here, is 18 feet. The cylindrical tank is being filled with barley at a rate. Okay, so now this is key, somebody's rate. If you're filling it, it's a 3D object. If you are filling it, you are referring to its volume. So the change in volume with respect to time is going to equal 45 cubic feet per minute. How fast is the depth of barley? So at some point, it's got changing amounts. It's going to increase as we go up. That means this length over here, that height is a changing length. As you fill it, it goes straight across. That radius does not change. So that radius is 18 feet. How fast is the depth increasing? That's this one we're talking about. So that means the change in the height with respect to time is unknown. Going back to geometry, volume is area of the base times the given height. On these related rate problems, what's really, really key is if you have a quantity that is fixed and not changing, before you do any derivatives, it is better for you if you plug it in because it makes the deriving and the work easier. So I'm going to say V equals pi times the radius squared times the height. The height is changing. That becomes 324 pi times h. Well, now I don't even have to use the product rule because I've gotten rid of a variable. I'm taking the derivative of volume with respect to time, and it's going to equal, this is all just the constant multiplier, so the derivative of h is its derivative with respect to time times that front constant. We know dv dt is 45. Plugging in. So then to solve for the change in the height with respect to time, I just have to take 45 and divide it by 324 pi. The label for this one, we go back to how things are labeled. This is in feet. This was in cubic feet because it was volume. Changing height is a linear dimension, so that's going to be feet per minute. Number 4. For this one, I can't draw a 3D sphere, so I'm just going to go through, read the problem, and pull out the information and make a list over here. What do we know? This is just the setup, no information for numbers. Mr. O'Connell is blowing air into the balloon at a rate. So there's a derivative. If you're blowing air into the balloon, that's three-dimensional. Look at the label. It's cubic inches. That means there's a change in volume with respect to time, and it's a positive 3 cubic inches per second. How fast, that's a rate, is the diameter of the balloon increasing? dd, change in diameter with respect to time, is the unknown. Then it says when the radius, so when we're at just 4 inches for that balloon. This one, sometimes you're given the volume formulas for ones that are a little bit trickier to remember from geometry. If I notice, I have v equals 4/3 pi r to the third. Volume changes as the radius changes. So there's no plugging in for anything over here as a constant. I need to find the change in the diameter. Well, what's the connection between the diameter and the radius? The diameter is twice the radius. So in terms of the derivative, then, dd dt should be double the dr dt. So if I know dr dt, I just have to double it. And I have a function here in terms of r. So dv dt equals, all these constants are going to be multiplied by this one's derivative. So 4/3 pi is being multiplied by 3r squared times the rate at which the radius changes. Well, what do we know? We know dv dt is 3. Over here, I'm going to clean it up a little before plugging in as well. So that's a 4 pi. And then the radius that we care about is 4 inches. And then dr dt is what we said we needed to find. When we solve for dr dt, here, we're going to get 3 divided by 64 pi. Make sure that the pi is clearly denoted in the denominator. Has to be clear. Then dd dt, what I'm looking for is double this, so I have 6 over 64 pi. And we don't worry about simplifying unless you're trying to match it up. A change in a diameter is a linear dimension, so I look at the units that I'm using so far. Linear dimension for diameter would be equivalent to the rate of the length in the radius, so it's going to be inches per, and then my unit for time is seconds. Number 5. You have Mr. Flaherty, and then you have a street light. So what's going on is you have the ground here. The street light, we'll say, is the furthest away, making, again, a perpendicular segment. And it's a fix. The street light's length is not going to change, so that's going to be 18. What happens is you have Mr. Flaherty walking along the path, so that's Mr. Flaherty right there. And then he's working towards that street light. So what happens here is that you take and you make a big triangle out of it. Mr. Flaherty is not changing his height. He is 6 feet tall. Then we look at what we're given. We have him walking towards the street light, and what happens is he moves, whether it's this way or this way, the light comes off, hits the top of his head, and casts a shadow. So this is considered to be the shadow length on the ground. So we can use S to represent the shadow length. And then you have some X distance over here that's changing because he's walking. Well, the connection, at what rate is the shadow length changing? That's this. So the ds, the change in the shadow with respect to time, is what I don't know. There's a walking rate up here. The walking rate is this distance, so that means we have dx dt, and that walking rate is 3. The connection for this one, take a moment and think about what connection would I use between all of this information before I take and do the derivative. The connection is similar triangles. You have a big triangle and a small triangle, and they're similar. So I would say 6 is to 18 as the shadow length in the little triangle is to the sum of those two distances here. Then simplifying, this is really 1/3, so that'll make life easier. Cross multiplying, 3 times s is equal to 6s plus 6x. I have some like terms, so I'll bring it over. Negative 3s is equal to 6x. Then what happens is I am taking the derivative with respect to time. So negative 3 is a constant multiplier times ds dt is equal to 6 times dx dt. Now because he is moving towards the street light, his distance is shrinking, so this is a negative 3. Negative 3 times the change in the shadow is equal to 6 times the negative 3 for the walking rate. Dividing out, I get ds dt is equal to 6 and I have a mistake somewhere. Oh, I used 6's here when I cross multiplied, and it should have been 1's. My apologies. So those are 1's. Those are 1's. The dangers of simplifying and not doing a new line of work. See? Lesson learned here. All right, so then we have just dx dt over here. And that means that is gone, and then I have to change up my like terms here, so that's a negative 2. And let's see if I have anything else. Subtract that, that's x. There we go. So now the negative ds dt becomes negative 3 becomes negative 2. And so now when I find the rate at which the shadow length is changing, I'm getting 3/2. And for a label, we have feet. We're traveling in seconds, so it's feet per second. So lesson learned, if you simplify, make sure you do it on the next line, because look how easy it is to just, boom, make a little mistake.